and thanks a lot for the invitation to this very beautiful location here. It's a pleasure to be here, and it's also an honor to open the second week of talks. The organizer basically asked me to present a very short talk of what should have been a very short side project. And this is investigations of two-dimensional adjoint QCD. And the reason why it turned out to be much more difficult than expected is basically because if you come from QCD, this looks at first like ordinary QCD from the numerical results that you get. So it seems like you have a confining theory, you have confinement-deconfinement transition, until you look more closely at the theory. And one of the messages of this talk is therefore that it's always very good if you're doing theoretical work to also confront this with numerics and check this with numerics, but also if you are doing numerics that you also keep in mind to understand as much as possible about the theory behind it, because these don't always tell you the whole story. So basically, this work, just to add, was done in collaboration with Mithat Ünsal and Stefano Piemonte. And basically, several years ago already, Mithat just asked us to simulate this simple two-dimensional theory. And then, much later, we decided that it might be a good way to test a new code that we have developed, because it should be such a simple theory. I mean, it's just 2D. And, but there were also other motivations for us in particular. Because one of them is that we are focused on studying supersymmetric theories, and some of them very interesting supersymmetric theories in the context of gauge-gravity duality are in 2 dimensions. So you want to understand more of the theoretical context of these theories and what kind of effects you might expect in these 2-dimensional theories. Then also we have studied compactified theories, and this also in a certain limit puts you to this 2-dimensional, back to this 2-dimensional theories. I mean, in both cases you have additional scalar fields on the game, but again, it's still similar. And more generally, this theory is said to be simple, but not too simple. So it's not like other 2-dimensional theories where you know immediately how the theory works, or can at least answer some questions in the large n limit, like it has been done for the Toft model. And from the lattice perspective, it's also an ideal playground for algorithmic developments. I mean, most of the quantum algorithms, etc., are usually developed for the Schwinger model, so it might be something else to look at, some other interesting theory. But I must stress that several of the features are much different from the QD counterpart, as we will see in the following. So we were not the first ones to consider this theory, so there has been a long list of literature and investigations of this. A lot of people in the audience did some investigations of this. So the first motivations came from string theory and confinement, and then also some supersymmetry was found in these theories. That was kind of an emergent supersymmetry at a certain value of the parameters. Then later on, confinement screening behavior of the theory has been studied. Also the semi-classical calculations, I will comment on later a little bit, have been done by some time ago. And recently, people have started to study this theory from a different perspective, and these are additional symmetries and deformations of the theory that have been not really considered in the first place, and also what kind of additional operators are allowed in the theory. A lot of work has been done concerning discrete light cone quantization, and more recently also Hamiltonian lattice formulations, and this will be covered in the next talk. There has been already some lattice study with Wilson fermions, but these are basically no results presented in this very first studies. And there are also related study of supersymmetric theories, which should be seen in this context, because it's believed that these supersymmetric 2-dimensional theories behave very similar. and of course much more further. So the basic theory is just adjoint QCD with one Majorana fermion in the adjoint representation. The Lagrangian is written down here. You have to consider, especially if you are in the lattice, additional deformations of the theory. One of them is a mass term, which breaks the discrete chirosymmetry that you have with Majorana fermions. And then you have also, which is a feature of the two-dimensional setup, you might have additional 4 fermion deformations of the theory that you have to consider. What is important is that center symmetry is unbroken with these fermions just because they are in the adjoint representation. And later, in recent studies, it has also been, there have been more investigations of these 4 fermion interactions here, and in particular it has been argued that there's an additional non-invertible symmetry in this theory which forbids the generation of these terms. But since we are not, we cannot guarantee such kind of symmetries on the lattice, we don't consider this. The infrared behavior of the theory is basically an open problem, and this is basically one main motivation why Mithat asked us to simulate the theory. So usually in two-dimensional theories you have a kind of linear potential which is quite natural. Here it has been predicted in these earliest studies that you have rather a kind of screening behavior in the quantum theory, and but if you add additional mass deformations of features, this quantum screening behavior gets lost. And the same is true if you add also this 4 fermion deformation. There's also believed that this gets lost. And by Alexei, it has been argued that if you just switch on a little bit of this 4 fermion terms, they could increase by the RG flow. So you're not guaranteed that these become small or irrelevant. And what has been found in these related supersymmetry theory studies that I mentioned previously is that basically you have a linear rise of this static quark, anti-quark potential. And the basic expectations is drawn here. So in the pure gauge case, you can basically calculate, the static quark potential analytically, where you have this linear rise. And then if you lower the mass, then you are expected that at long distance you get a kind of lower string tension until you might finally reach, in the massless limit, a screening behavior. So no string tension anymore. And the question is now what happens with this 4 fermion deformation, and there you can end up anywhere. Just from our experience here is that these seem to have little influence. I will come to this later. And so one cannot really distinguish them from this screening behavior. Yeah?
Concerning RG, I think whether they increase or decrease towards the IR depends on the sign of C2.
So as I said, it might, but it's not known, especially if you go to the non-perturbative domain, what happens if they really increase and become relevant here. And this is basically the motivation for our study. We want to see how much of these effects are seen in the actual simulations.
Quick question.
Yeah.
Is it defined, are we on a torus, are we on a sphere, plane, what are we?
So I come to that. Usually periodic boundary conditions and anti-periodic in one direction. Yes. So I do not have time to cover all the details of this approach. Just to mention, it's a standard Wilson plaquette and Wilson fermion action used in the simulation. So we break chirosymmetry due to an additional term, which is this Wilson term, add in this case a formulation. So you have to recover chiral symmetry by fine-tuning. We have also, I will present later, also some results with overlap fermions. They have the additional feature that the chirosymmetry is intact on the lattice, So you don't have to worry about this. We use the standard RHMC algorithm, and we have covered a wide range of beta. Usually I will use the Toft coupling later in the diagrams and everything can be expressed in units of this quantity. Yeah, the issue with these Wilson fermions is, as argued by Alexei, that they can introduce additional four fermion terms, and then the question is whether they are increased or decreased due to RG.
Sorry, the next question?
Yeah.
So in principle, you're also going to generate higher order terms, not only 4 Fermi, but 6 Fermi, 8 Fermi. Is there a reason that we stop at 4?
I mean, these are the just from dimensional grounds, the terms that you consider in this.
Yes, the other ones are irrelevant in the UV, but they usually have very large number of dimensions, so they can become relevant in the IR.
So there are some kind of terms like this Wilson terms which are kind of dangerously irrelevant. They break symmetries and may therefore introduce some additional terms in the IR. But the only term that basically is of this form is this Wilson term.
This one doesn't, but this term also generates 6 Fermi and higher, right? Or
it might generate, but the relevant terms it generates are these 4 fermion terms, and these are important. Yeah.
Question, I'm actually confused. In which sense would the 6 fermion terms have large anomalous dimensions near the continuum of it? It's hard to see.
I think that was one of the conclusions in the paper by Zohar. I think there are like exponentially many vacua, and they come from higher order Fermi operators. They become.
I read that paper, but maybe you don't know.
Yeah, we can discuss afterwards. That would be interesting if such kind of terms become relevant. I mean, in general, you have to assume something about the fixed point structure in this general theory space, and of course there can be non-perturbable effects where things get important, but this is not what would be naively expected here. So the observers that we consider is first the Polyakov loop, which basically tells us whether we have a breaking center symmetry. It's just a product of these link variables. Then we consider also the chiral condensate as a measure of spontaneous chiral symmetry breaking. We consider Wilson loops to extract string tensions. And then certain meson operators where we extract masses from the exponential decay of these correlation functions, these operators. And one of these operators, or one observable related to these mesonic states, is used to do the mass fine-tuning. I can later on explain in more details if you want, but this is just a brief setup. So the first thing you want to look at are possible phase transitions, because you want to know where you are with your simulations. And this is, basically you do a scan. So you vary this number of lattice sites in the temporal direction, where this temporal direction with antiperiodic fermion boundary conditions is basically inversely related to the temperature. And then we also studied periodic boundary conditions for the fermions. With antiperiodic boundary conditions for the fermions, you see that this is SU6. So you see this clustering around center broken vacua. So it looks like you get a finite expectation value of the Polyakov loop, and therefore center symmetry breaking, so a deconfinement transition. And with periodic boundary conditions, this seems to be absent. So everything like in QCD. But there is a caveat, so you have to look closer at these theoretical explanations. And in particular, you can go to the small circle regime, so to the high temperature regime. And there you can do a semi-classical analysis. And the semi-classical analysis is basically governed by the potential that is introduced by the fermions in this case, because this is the relevant contribution here. And with antiperiodic boundary conditions, you really find this center broken vacua in this theory. But what you have to consider in addition to this are quantum effects by instantons, which are tunneling between these vacua. And the important thing is that these tunneling events happen with this kind of probability. And this is not, so the constants that appear here are just related to the SUN gauge group and then this temporal extent, so the temporal circle size, but there's no scaling with a volume. And this is what you will need to have a real phase transition. You need a suppression of this tunneling rates with the volume. What you have, so there's no phase transition in the usual sense in this large volume limit where you suppress the tunneling between the vacua. And what you have instead is that you have a scaling with a number of colors. So you have a phase transition in a sense when you increase the number of degrees of freedom by just going to the large n limit. And so you can study in more detail than the finite volume limit by increasing this number of spatial lattice sites. And what is happening there is rather weird. So you basically see that you lose your signal for this deconfined transition, which is shown here in the histogram of the Polyakov loop at this peak different from 0. And then if you increase the volume, usually these tunneling events are suppressed, so you get an enhancement of this peak. But here the opposite happens, so you get more and less of this peak, and you get in addition in this, if you do this infinite volume limit, you will get that there's no real transition here. But what you get is a transition in the large n limit. And this you can also observe here. This is the average absolute value of the Polyakov loop as a function of the temperature in units of the Toth coupling. And you see that basically this observable rises more and more steeply the larger the number of colors. We went up to 8 colors here. And then you see also in the susceptibility an increasing peak here with the number of colors. So there's a really a scaling to a phase transition. Yeah?
Just check my understanding. So I think this kind of washing out of the would-be phase transition it's not just true for adjoint QCD, it's for any theory in 1+1 dimension, right? It's just Coleman, Merman, Wagner applied to a discrete set. I don't think it's special. Like, you know, if you're in a 2D theory, when you compactify in a circle, you're in quantum mechanics. There cannot be phase transitions in quantum mechanics, unless you take the large limit. This is not special, right? To QCD.
So with a large n limit, you can still have.
With a large n limit, you can still have. So I'm not disagreeing with this. I'm just trying to understand what is special to the adjoint QCD.
Yeah, no, this happens for many theories in 2 dimensions. And also, I mean, Mermin Wagner is something different. I think this is for continuous symmetry.
That's true. That's true.
This is something different, but I agree that this is quite a common feature of this low dimension theory. So this is for this phase transition of the Polyakov loop, and then you can also look at the chiral condensate. Here you have the problem that Wilson fermions have a problem to get the absolute value of this fermion condensate, but you can still study the temperature dependence. And what you see is basically at higher temperature it goes down and reaches a plateau at low temperatures. Which is expected kind of from earlier studies also in the semi-classical domain. It's expected that this goes finally exponentially down. If you look at the individual configurations, it's remarkable that basically at low temperatures you have a certain fluctuation of this condensate, and then the average value gets down at higher temperatures, but you have it also gets more scattered, so you have some separate peaks which get higher values. But
I thought that this condensate is non-zero only at 0 temperature, and there is some mechanism why it gets destroyed with any non-zero temperature because of the name walls.
Well, you can calculate it in the semi-classical domain, and there you get contributions from the instantons.
At least in the infinite volume limit, it works. But I may be confused.
Okay, we can discuss it afterwards. So what you can now do is you can more closely investigate this condensate, and you will see that in the small circle regime, the main contributions of the condensate come from the values where the Polyakov loop is small. And this is also kind of expected because this is the regions where you have these tunneling events. And these tunneling events are basically determined in terms of the Polyakov loop by zeros of the Polyakov loop as a function of this spatial lattice extent. So you have here two configurations which have low fermion condensate, and then you have one with a large fermion condensate, and you see that you have basically two tunneling events. And then you can measure on the lattice also the zero mode contribution, and you see that this is nicely peaked exactly at where you have the zero of this Polyakov loop. So the main contribution to this condensate that you calculate in the semi-classical region is basically due to this tunneling events of the Polyakov loop, which are determined in this case by the Polyakov loop. Okay, now we wanted to get also the condensate at zero temperature, but this has problems with Wilson fermions because they break chirosymmetry, therefore you get additive and multiplicative randomization of the condensate. So if you want to determine an absolute value, you have to use a different approach, and what we used, we were able to do a reweighting. So basically we switched from Wilson fermions to overlap fermions, and they implement a chirosymmetry on the lattice. There's still one additional issue that you have to solve, which is how to take the chiral limit if you want to compute a non-zero value of the condensate. If you first take the massless limit and then the infinite volume limit, you will always end up at zero. So you have to first take find a certain range, and then you have to go to the infinite volume limit, and then you have to extrapolate to the chiral limit. And the result is actually in quite good agreement with other methods, and also, interestingly, quite close to what's expected, just with some additional prefactor to the Schwinger model. Now, the last part, the most important part, is of course to study the confinement properties, and as I said, this will tell us about the relevance of the fermion terms. We do this by extracting the static quark, anti-quark potential from the Wilson loop. We also did this using Kreutz ratios, but this I won't discuss here in further details. And what you obtain for this static quark, anti-quark potential is basically, this line is this exact result from the pure gauge limit. And then you see if you lower the masses, this kappa is some kind of inverse mass parameter, you will get smaller and smaller values of the string tension. And finally, you cannot really tell whether a linear fit is still applicable or whether you should rather do this screening approach, and whether this is completely new data. So here it's just a fit done with the screening form, but we also tried another approach, which was just to fit the large distance behavior always with a linear behavior and determine the string tension. And then you can try to extrapolate this towards the chiral, so the massless limit, and it seems to agree, at least with a given precision, with zero in this limit. And similar results we have also obtained for SU3. Now, the question is, of course, how much, what is the scaling towards the continuum limit, because we are still at a finite lattice spacing, and this is shown in this plot. Basically, you can change the lattice spacing by changing the gauge coupling. And this shows how different results for different gauge couplings nicely fit on a single graph. So for two different masses, this is a scan of beta from 15 to 200. And so this is the inverse gauge coupling. And all of these results seem to lie at most closely on top of each other, so there's not much effect from going to the continuum. Yeah.
Have you looked at the large N behavior of these kinds of plots?
We have checked SU3. We have also checked further SUN, but it seems, so for SU3, it also seems that that we get a similar behavior, an exploration of the string tension to 0. But for larger N, it becomes more and more challenging because this screening behavior seems to set in later, or
That's consistent with your statement about the polycoupled behavior, because you can presumably get this from the polycoupled correlator. In fact, maybe that's how you got it.
yeah. We also, so this is from Wilson loops, but we also checked the polycoupled correlator.
Given that the polycoupled expectation value vanishes in large on one side for large beta and on the other side,
Okay, yeah.
then you might wonder that at large N something very interesting is going to happen to all. In fact, which I would find very confusing given the beautiful results of Igor and Zohar and friends. I actually don't know how to make sense of any of it. So anyway, maybe we can discuss later.
Yeah. We also have results for the bound state masses. So in this discrete light cone quantization, the mass of fermions and basically bosons have been determined previously already. So we wanted to have something to compare with, but I'm not so much proud of these results because they can be improved, much improved by using more advanced techniques. For the fermion operator, we've chosen something that is not really present in the theory. One should rather consider baryonic operators here, that they are more difficult. We considered a meson, a scalar meson in the bosonic sector, and somehow within this larger uncertainties that we currently have, this is consistent with the discrete light cone quantization, but as I said, these results need to be much improved. I must say that all of these states are very hard to measure on the lattice because what is called disconnected contributions. So you have, if you measure, for example, something that is similar to a pion in QCD here, this is much easier and gets several orders of magnitude better results, smaller errors here. Okay, and this brings me to my conclusions. So, yeah, the lattice results are so far consistent with the semi-classical analysis. I've shown you this where you can nicely map this to the semi-classical analysis. We have also seen that they prefer some screening, but it's if you go to the chiral limit, but and no evidence for the contribution of the four fermion operators, at least no large contribution. This has to be taken with a grain of salt because we just had a certain parameter space and a certain range of lattice sizes compared to the cutoff. So if you are looking at the RG perspective, there is much more to explore in the whole parameter space. We have seen a formation of the chiral condensate, and further things that one could do, of course, is to cover this, try to cover as much as possible a larger range of the theory space to really make some more statements about this fermion operators. They can also be measured directly. We have now only indirect access to them by looking at how the string tension behaves, but one can also measure them directly. And of course, this bound state results can be much further improved. Thank you for your attention.
Questions?
How hard is this all numerically? What kind of resources does one need to actually use?
This is not so hard. I mean, the simplest case can be done just on a laptop, but if you want to have these results for the string tension where you need Wilson loops of larger sizes to get, then it's better to use a smaller cluster.
Let's say you have the overlap fermion
Yeah.
at the physically massless point? Even that can be done on a laptop in this case?
A little bit larger than a laptop, but still kind of something that fits under your desk. So it's not, it's not kind of a
That's awesome, actually. It can be done under a desk, even that.
So yeah, I mean, again, then you have also to consider that to get a first idea of the theories, you have to do a large scan, so you want to do things in parallel. You don't need a big supercomputer center.
If there are no further questions, let's thank the again. And now we have a double header.